So thank you very much for inviting me and giving me this opportunity to present some of our work. This is a very small portion of our work. Naturally, you can imagine we do much, much more. And it was really difficult to actually select a topic because we could be speaking on many things. I have, however, modified the title slightly. It's actually, I snuck in Cloud Mesh multi-cloud interfaces because this is super relevant for the NIST architecture and its long-term projective into the future. And my name is actually Gregor, and I have a fairly easy to pronounce last name, but difficult to write, so I don't expect that you memorize this. My last name is actually phonetically pronounced as von Laszewski. Think about it as the La chef and ski. La is the happy cook that skis, so you can really remember this quite nicely. Or if you actually do look up in Google and type in the words Gregor and cloud, or Gregor and Cloud Mesh, you will actually find me. So this is an easy way to locate me. And one of the things I did is I put here my email address up, as well as my homepage, which is fully hosted on GitHub. So I utilize that. We have a manual for our Cloud Mesh software that is part of this work. You can contribute to our efforts, not just the Cloud Mesh effort, but also the NIST effort, because I'm also a chair of a subgroup in that NIST effort. You can certainly collaborate with us. So even if you don't contribute, you still can collaborate with us. And naturally, we are there for hire. So you can contact us and we can do projects with you together. What do I want to talk to you about today? First, I would like to give you an introduction to the NIST Big Data Reference Architecture. This is not only relevant for Python, but for other frameworks, because NIST makes it a point to not champion a particular technology or programming language or framework, but tries to address things in a more general framework. In particular, I will be talking about the volume 8, which I was an editor on, and I'm happy to announce that NIST last week has accepted that volume as publication. So last week, but it's not yet on the website. And so I will be putting up some links, and you can look them up later which, in the video that is being online available to find out where this is. But NIST will update the volume 8. One thing that was important to us is that we are not only working together with NIST to come up with a proposed document that describes this, but to actually verify if what we are describing can actually be implemented and utilized. And there are two parts to this. The first is the reference implementation that we do as part of Cloud Mesh. And the second part is how do we do the analytics services on Cloud Mesh. And we have, at this time, only one service that actually showcased that this does make sense. Here's a long list of documents and pointers. Again, you will have access to these presentations later on, or can look on my webpage, and these pointers will be made visible there. I would like to point out that the first one is the working group from NIST. And there is currently an outdated volume up there for us, but they will be updated within the next months. And if you already want to look at the new volumes, just take a look at my Cloud Mesh github.io website. There is a NIST repository that does have the PDF. And since we are working with Generation Z students that also, and esteemed colleagues that only travel with iPads, we also have thought ahead of time and put EPUB publications down, so you can download them right on your iPads and tablets to read them there. The evolving documents is really important. I have a fairly large number of documentation, so on the order of 1,000 pages or so. If you want to teach some people Python and cloud computing, so you can leverage that, and they're all freely available, and you can invite me to your companies and I can give talks. I would like to acknowledge support from NSF, from NIST, Indiana University, and actually I would like to also acknowledge myself. I should be putting my family there too, because I do a lot of these things in my free time, and I'm not getting actually paid for what I sometimes do. Let's jump directly to the NIST Big Data Reference Architecture documents. This is a document series that introduces people from industry, academia, and other communities to big data and what it would take to define a reference architecture so that others could be implementing them within their companies or within their educational frameworks. As part of this, we need to be first identifying what are the definitions to big data and those things. So we have a full volume dedicated to definitions. We have another volume dedicated to the taxonomy for big data, which I will not be having the time to introduce today. Then we have a fairly large volume about use cases, and you can contribute these use cases also to NIST as contributors. And these use cases are also being now moved into other standards bodies, and they have accepted those as part of that effort. The volume 6 describes the actual big data architecture, and I will be showcasing only one single slide from that particular document, which is the architecture picture. We address security and privacy concerns, and then the rest of the time I will be spending on volume 8, which is the reference architecture, and that has actually a pretty big implication, because we couldn't just publish the standards without testing out if this thing actually does work. So that's really important. Now, that means that the volume 8, the interfaces, gets input from all these other volumes. So it's a lot of work to go through these volumes and make sure that they're consistent and work with each other. But there is an additional thing that goes beyond what NIST is doing. That's the cloud mesh reference architecture. In a matter of fact, this reference architecture has also been deployed as part of one of the largest supercomputing educational resources in the United States, which is in San Diego. And we do on that particular cloud a cluster on demand. So while we're integrating, for example, in Slurm, virtual machine hosting in Google or whatever other things you do, but on this particular cluster, we actually deploy an entire virtual machine set as a cluster for you, and you have full access to a virtual cluster, and you can utilize that. So that's very different from OpenStack and other things which do not leverage, for example, existing queuing systems such as Slurm. This makes it possible that we can do on-demand scheduling of, for example, a virtual cluster for someone if he has a biology experiment or so. And I developed with my colleagues together the client interface to it, because as we saw from the Jupyter example that we had here earlier, it's impossible for other people to memorize what needs to be done in order to put these things. So our command to start up a cluster is this: start up a cluster. So, and then you get a cluster. You have a parameter. It says this is number of nodes. Start up a cluster with 50 nodes. And then you get a cluster with 50 nodes. So let's skip directly to the volume 6 that introduces the NIST Big Data Reference Architecture. What we have discussed with a group of, 40 or so people, mostly industry, how they would approach, for example, an architecture that addresses big data to be implemented on their infrastructure. So we have on the bottom, for example, big data framework provider that may be providing a batch queue, an interactive queue, or a streaming queue. We have platforms such as, for example, index storage or file systems. And then we have on the lowest level the infrastructure services. That's where I'm traditionally coming from, where we have virtual resources and physical resources. Naturally, we need to communicate between these components with messaging, and need to be also integrating strategies for resource management. All this is embedded on a security and privacy framework and fabric, so that you can make decisions about, okay, do I want to expose this to someone, or do I not want to expose this to someone? And you can essentially pick and choose from this. And that is embedded, again, in the framework, in the management framework. On the top layer, we have big data applications that utilize this particular big data framework from providers. And as you can see, there are multiple slices. That means we have multiple providers. There's not just one provider, but there could be multiple providers that do this. And we have also multiple big data applications that pick and choose whatever they need to do in order to figure out what their particular application requires. So one of the things that we actually have done is we have developed in Volume 8 our interface to this particular graphical architecture picture that I put out. And we have introduced things such as identity, data, virtual clusters. Virtual clusters really important to us. This is, nowadays you just use Kubernetes in many cases, or Docker Swarm. But when we started this effort like 5 years ago, these systems did not very well project this thing, and so we came up with I think we are the first group who came up actually with the term virtual cluster, and Comet is an attribute to that particular implementation. We naturally want to also represent infrastructure as a service, compute services, containers, deployments, MapReduce, microservices, and others, such as, for example, analytics frameworks and pipelines that we would like to specify. One of the problems is I have worked previously in a standard body, and we had the issue that the contributions from the community came in so rapidly that the modification of the document took months to do, and this was also the case here. So what I actually came up with is I developed a framework that actually takes the specification from the document and delivers the implementation out of the specification document. So this way we can do a specification and then immediately test the specification out and see if this is something that could be utilized. I wish I could spend more time on this, but so this is just for me. I did that. It's not something formal, but this has been super time saving. One of the things we need to be thinking about, what's the scope of this document? We have established operational interfaces. We describe how they are being defined so that other people can recreate this and put their own backend frameworks into this. And we can actually set interfaces through examples as part of the definition of such documents. The content is really done through a formalization of the interfaces that is being specified in OpenAPI 3.0. And is anybody here aware of OpenAPI? If you could just quickly raise your hand. None. Okay, that's a surprise. One person. Okay, so that's a surprise to me. It allows us to specify interfaces in a very formal fashion, while we don't have to buy ourselves into supporting just Python. We can take the OpenAPI specification and derive 30 to 40 programming languages out of it because we are using a generalized framework. And this is what NIST actually has approached me with when they started with this effort. They knew I do stuff like this. And what we can actually do is we can take that specification, and through community tools that are being developed by other people, we can develop a Go interface, a C#, a C, a Python, a Java interface from that same specification, deriving then services that are running in that particular language. So if your shop is doing Java, then you would be exporting this to Java. If your shop is doing Python, you would be doing this to Python. So one of the things that we have done is we have actually used our expertise from the development of Cloud Mesh, and I have to mention to you is I'm actually very little known in the community. However, or in the cloud community. However, this particular tool was the very first multi-cloud interface ever. So so even if you talk about Terraform and all kinds of other things, we have done this 5 years before they even started thinking about this. Doesn't mean that my code is better than theirs because they have financial backing from companies. I don't. I'm just doing this as a silly academic in this free time. And so one of the things that we actually do have is we have interfaces to go to Amazon, Azure, Google, and Oracle. And right now we are in the phase of re-implementing some of these interfaces to make them better, so that they can also be utilized by anybody. And this is where you can collaborate. If you want to contribute your interfaces, you can actually do this with us. And we can put your cloud into the framework. One of the things is we are using REST, and I will talk a little bit about REST interfaces and why we are using them, but they are not required as part of the standard that we are pushing forward. We have a number of objects. This is an initial set of objects that we put into place to get some thought about what should be included in such documents, for example. And this thing can naturally grow if we were to, for example, put the analytics framework in there. So we see then we have things like k-means or SVM and so forth popping up that could be integrated, but we haven't done that because we need to be releasing the documents so that the community can contribute to them and can do the next step. One of the things, as I already alluded to, is I have developed a pipeline to get from the specification directly to an implementation, because we are using a specification that is using Open API, and then we can directly derive the web services out of it. And so when we make modifications to the specification, it spits out new web services. So we have everything hosted in GitHub, where the specification is there formulated as a document in the source, and we can generate PDF and EPUBs. And then we take the specification and use that particular specification in Open API, read the schema, and produce REST services that we can utilize. I do everything in Python, but that doesn't mean that you couldn't do this in any other language. So we do everything in Open API, and Open API is somewhat simple to understand. However, it's a little bit more formalized, and so when you, as a person, look at Open API, you start thinking, okay, I have to spend now 50 hours learning that. I don't have the time for this. But it's actually really simple once you get a hold of this, and Open API is one of the community best practices that is being employed to develop, for example, REST services as far as I can see. However, I've learned now different because you guys are all from industry, and so I see the best practice is different. So I need to learn from you how you do this, and we discussed maybe we set up at one point a survey so that we can figure out how, for example, I can modify my strategy or the classes to address, for example, your needs within your companies. So what's REST? You probably, I guess everybody knows what REST is, so I will not actually say much about this. But the one thing is we have to recognize that this is not a standard. And when we use REST in our specification, we don't actually use this as a specification as a standard, but as an example on how do you formulate, for example, an API or an interface. So the specification doesn't say you have to do it in REST. But this is just one of its implications that you can do it if you want to. Open API comes with a bunch of logs. It's actually a YAML document or a JSON document, and there are things like an information, how do you specify a server, how do you do security, how do you path, and how do you specify the components. And I run right now into a more detailed information about this. I've decided to showcase you how do you, for example, develop a REST service that that uses OpenAPI to return the CPU info from your particular computer. This is actually a pretty interesting example because it's a dynamic example. And when we are talking about data and big data, it's not enough to look up in a database that is being updated, but in many times you actually have to interface with streaming services that are producing data live at that time when you invoke the service. And so this is a placeholder for that. Everybody showcases you typically databases, but we need to be thinking beyond databases when we are talking about live updates. So here's a YAML specification that, for example, says, okay, this is the beginning of the document, and I host my thing on the server. As you saw from our earlier examples, people need to be reminded, where do I actually put in, what do I put in into my browser? And that's basically your reminder about what you need to be putting into your browser. Then we need to be specifying the path for the REST interfaces, such as, for example, what's a GET method, and you probably all know what a GET method is. And when you look at this particular code, we just do some documentation. We have a summary. We have a response to that particular GET method. What should actually happen when I execute this and I run it into certain conditions? And one of the responses that I have is this is the response 200, where my is essentially a success, saying this is my CPU info. One of the things that we have done in the specification is also we integrated something called an operation ID. And this is a feature that is part of the public domain tool that we actually use to convert this specification to a Python program or any other program that now says this is develop me or spit out a template for a function that's located in the CPU directory, but the function is called getProcessorName. So this is, I have implicitly included now a namespace into the specification, and now it's up to the developer to implement that getProcessorName function. Naturally, if you use a Java program, you do this in Java. If you do this in Python, you do this in Python. So we can do this for many other things, and then one of the things that we really need to at the end is we actually have a noun as part of our REST definition. What are we actually storing? And in our case, we have the CPU that, for example, has a model, and one of the model, for example, we put in the string. Another would be the value for the CPU value. Now, the fascinating part about this, once you actually write this, we are utilizing, for example, a connection, the software connection, and it spits out when you read in, for example, this line up.add API CPU.yaml. This is where our YAML file is being written, a full-fledged REST service. So this means that with 10 lines of code and the YAML specification I have there, I have defined a REST service. This now becomes super useful if I am specifying a document that says, okay, this is my standard that I would like to everybody follow in my company or in NIST or in my university. I follow that, and then I'm spitting out with 15 lines of code a REST service on this. Not only can I do this with one service, such as CPU example, but I can do this with any service that I specify. And so therefore, I have a scalable framework for defining any interface to any service that I want to do. Now, one of the things that we have actually done is we have actually leveraged from our previous work from Cloud Mesh, which has its own architecture, and the architecture is very simple. It's a layered architecture where we leverage platform as a service, HPC abstractions, containers, and infrastructure as a service, and expose this to a Cloud Mesh client. The Cloud Mesh client is our API in Python that exposes all of these services to a Python API. And I don't claim that we have completed that implementation. That's naturally an academic project, but we can make that more stable in case there is some wishes being formed. This is, I would like to see this or that or the other, and then we can integrate this. We used to also have a Cloud Mesh portal that integrated this whole thing as a portal, but we no longer support that because we found the client API so useful, and we means me. So I made the decision at one point, I don't have the time to develop Drupal, Flask, and Django portals. It's just too much time on our hands. We need to be focusing on the bare stuff that provides functionality. So through Cloud Mesh, we can now integrate Cloud Mesh in these operations IDs that I've actually showcased you. So this means I can now technically say this is a start up a cluster in, for example, San Diego, through me defining an interface. And the interface is a REST URL, basically. And through the URL, I can actually start an entire cluster in San Diego with 10 nodes. It's no problem. I can do the same thing on Amazon or on Google if we were to be facilitating these interfaces. So why is this also useful? This is, we have heard already earlier about the continuous integration. So we can naturally do a deployment abstraction. And that's what we need to do next. This is we can not only develop these services, but we need to be deploying them onto a real hardware and software. So what we then can do is we can use the GitHub, publish this stuff there, use maybe Ansible, Chef, or Heat, and put some data on this to create deployments on different architectures to verify if these services are compatible on all of these infrastructures. Good example is typically people use Azure and Amazon, and so this way we can verify if our services run on both and what performance hits do you get when you're using the one or the other service. This can then be integrated, or this has been integrated in our development for the NIST document, where we did the design decision on the very top, which is our volume. We derived from the volume through our Cloud Mesh scripting a specification and a deployment that we then executed on data, and then we tried them out so that we can verify if that entire process of defining these services does work. Here's an example, and I apologize for the small picture, so I may have to skip this. I'm not sure if you can read it, though. It's difficult for me to see. But this is a boot process, and I will be going into this a little bit later. So this is just a virtual machine, but it could also be applied to a Docker container, where we simply say, this is select me a particular resource. On that resource, I would really like to boot a machine. I need to get an image, I need to get a flavor, I need to start this thing up, I need to get something back. But I can also do this on another cloud. And the problem is that we need to be sometimes replicating these on other clouds, because I'm about multi-cloud environments. I'm not only about Amazon or Azure, I'm about all of them. So in order for us to do this, we have to then develop our provisioning activities, and these provisioning activities then, for example, integrate. How do you select the cluster? What do you actually want to have? CPU, memory, what software would you like to have? What software would you like to deploy? And so we stage such a specification onto that particular infrastructure. This was all fairly theoretical, and I'm not sure how many pages that NIST document has, because they're formulating it differently. I would guess it's 120 or so, something in that direction. So it's a fairly long document, but it has limitations, and the limitations can be found by you. You can contribute to this, and then we can make suggestions for NIST to improve upon it. So I would like to get to this example, and the example is the same problem that our colleague from earlier from Ball State faced. We have these students from biology, from the education department, that may actually study data science as their topic. Now, if you know about what it actually takes to put a virtual machine on Amazon, or on Azure, you typically say, use the GUI. Everything is being done through a GUI. But I'm dealing with 1,000 virtual machines. How do you do this with a GUI? This is not that scalable. So I need to be figuring out how do I actually teach them how to do that. And so the best way we found is we develop our own tool from the command line that actually is able to do something in that direction, or works towards that direction. So what we can communicate to the students is we can give them actually a configuration file for the class or for their project or for their problem, and we define this with them. This takes me probably 5 minutes to do while discussing the needs with the students or the faculty members that actually do this. And then I essentially say, okay, what infrastructure would you like to have? So on which cloud would you like to host this? Or where do you want to have your virtual machine being booted? And so what I can essentially say is okay, set the cloud to the cloud of a particular name. And the names are, for example, Amazon, Google, or whatever other things you do, and you can specify your own names. You could call this green eggs and ham if you want, but or something more useful like my transportation problem cloud or something like this. So the next thing is when you look at the Python API to boot this thing up, you will find that you have to deal with security groups. You have to deal with keys that you may have on your local machine and stuff like this. And if you have a key on your local machine, the only thing that you have to do with us is actually saying CMS VM boot, and it boots up the virtual machine. I have actually here a slight error. It's actually CMS VM SSH. We used to have a login, but I've replaced this with SSH. And then in case you want to manage the virtual machine, you can say CMS VM delete. As you see, there's no specification of any name for the virtual machine, which is for the user completely unimportant, right? Because he wants to have a virtual machine. This is a one-off example. So CloudMesh saves the name of the last started virtual machine, and I can actually do this, all these commands without me remembering that name. Completely unimportant for me. I can naturally specify the name as a parameter to any one of these things in case I have multiple ones. Not only that, I can actually put in host names based on bracket notation. So let's assume I want to define the machines Gregor 1 to Gregor 1000. I don't have to type in 1000 things like this. I simply say this is CMVM boot Gregor, bracket open, 1-1000. When opens up 1,000 virtual machines. And there's a color issue. The first one was supposed to be AWS, so CMS set cloud equal to AWS. How do you boot now on Amazon? Well, it's simple, CMS VM boot. Now you set the cloud to OpenStack, which we have access to. A cloud that has OpenStack. Now the question becomes to your student, how do you boot a virtual machine on OpenStack? If I already do a CMS VM boot on Amazon, I should be doing the same thing on OpenStack, so we do the same thing on OpenStack. Now I switch the cloud to Azure, and how do I know how to start a virtual machine? Well, CMS VM boot. So I can remember CMS VM boot, while I can't remember anything else anyways. And this looks up in your YAML file the default images that you would like to use. And we have made very good experience with this because at times the Amazon cloud went down, so we switched to an Azure cloud, or the OpenStack cloud was not available, and we switched to an Amazon cloud. So there is no excuse anymore for the students not to do their homework, because we can say this is the cloud. If the cloud goes down, please go to another cloud. I don't know how to do this. Well, how about CMS set cloud equal Azure and then CMS VM boot? And now I've eliminated 70% of our homework problems. So this is fantastic, right? So I can actually do this further, and we used to actually have 2 years or 3 years ago a really cool framework that actually did this, but we haven't so far implemented this into the new version of CloudMesh. But we want to, for example, host now a Hadoop cluster, which we need for big data analysis as part of the big data reference architecture to demonstrate that we can actually deploy, for example, Hadoop. So how did we do that, or how would we do that? So we did that in the past. So say, okay, select me the infrastructure on which I would like to host that particular Hadoop cluster. I say CMS set cloud equal OpenStack. And then I simply say, this is okay, create me the cluster where I have the name Hadoop cluster. I get 10 nodes, and I have the service Hadoop. And then I simply say CMS cluster deploy with that name of the Hadoop cluster, and it deploys that thing for you on that particular cloud. So again, this is not implemented. This used to be implemented. So we hope that the current generation of students for this semester may be able to do something in that direction. More on Cloud Mesh, I would like to focus a little bit more on I would like to go a little bit away from the NIST representation towards the Cloud Mesh representation, because when did I start with cloud? Exactly 10 years ago. So that's when OpenStack wasn't yet invented, and we still had eucalyptus and all kinds of other stuff. And some of these lessons that we have here is based on that experience that we have over 10 years of running multi-cloud environments. So we have already identified that we can easily manage virtual machines, but we can as well manage containers or interface with Kubernetes clusters if you so want, because if you, for example, want to say, this is deploy me a cluster with 10 nodes, we could be, for example, doing this with, for example, Kubernetes control commands and hide them into Cloud Mesh. So that's really, really convenient for us to do. We also need to be addressing hybrid clouds. This means we not only have a cloud in Amazon, but also maybe by a local computer or a cloud on-premise with which we are integrating. And this is the multi-cloud stuff that we already pointed out. Why do we do this? We have capacity, technology, and integration, federation, and robustness. If you take a look at this, on this picture, this makes it pretty clear. In multi-cloud environments, students sometimes get a free tier. And what we can essentially do is we can combine all the free tiers to one, so it's a cool capacity. And this is actually a good story, because I had one student that actually refused to shut down his virtual machines on the cloud. And within 2 weeks, he used 20,000 compute CPU hours, while the entire calculation was irrelevant. He used up the entire allocation for the entire class, and he refused to shut his virtual machines down. And so we no longer do that. So we just don't buy any hours anymore. We simply say, take the free stuff. If you don't get the free stuff, then too bad. Technology robustness. Naturally, when one cloud goes down, we can move to another, and we can leverage services from different clouds with each other. And this is important for the big data reference architecture, because we may have services that are hosted on one cloud but are not offered on another cloud. But for us as data scientists, it doesn't really make a difference which cloud we have. We want to have the functionality. So naturally, we can integrate things such as price transparency, availability, capacity, and vendor login as parameters to the motivation why we are actually doing that. And we need to manage this in some kind of brokerage fashion. So we start now integrating a project that we call Cloud Mesh Frugal, where we maybe find more cheap resources on data and compute. So this way you may want to move your data into a cheaper tier at a particular period of time or something in that direction. One of the things that we found actually is pretty cool too is we have developed as part of NIST the concept of, or actually as part of Cloud Mesh, and then integrated this into NIST, the concept of virtual directories. At times you may want to host your data in multiple services. Depending on where your analytics services are running, you may have to duplicate the data or so that you can start up the services on that particular cloud. Or you don't have enough resources, such as, for example, our students, they get the free tier and they can't store that much, And so what we did is we created a virtual directory in which we have a directory name, and in that we have a file being represented, and that file points to the appropriate cloud. But when the student uses this on the local computer and simply says, fetch me or list me that particular file, it goes out to the cloud, fetches this over to the local machine, and then you see this on just as it were a local directory. Naturally, if the internet goes down, you're out. We didn't build in any fault tolerance and so forth. But this is an easy student project to enhance. The same thing we did with the virtual cluster. So technically, we can actually do an IP address as the cluster, and we can move that into a virtual cluster, and that virtual cluster could be hosted anywhere, and we can do virtual machines or containers or whatever other thing you want to do. And so this doesn't have to be just a virtual machine, it can also be a real computer. Additional features that we are looking into, this is, for example, abstractions for compute, task, function, data, the access. For example, I prefer command shell and line. For that reason, I've pointed out already earlier in the morning that we have developed something called CMD5, which is a Python package that not only allows you to do an argv, but it actually runs a shell, and you can switch between shell and command line invocation. So you can have a shell that actually stores the status, but also command line. So this way we can, for example, say CMS set cloud equal to Amazon, and the next time I invoke that particular command, it actually is doing this. And then you can invoke the shell, which functions just like a MATLAB function. So there's a whole bunch of commands that we can do. You can do manuals and scripts. You can list flavors and set clouds and so forth. You can list the image. And one of the things that this is, if you go to Amazon, you, for example, find 94,000 images on Amazon. That takes quite a while to download and mine. If you would really like to do this like an academic, like I do, you may actually upload your own images, but we may actually mine 94,000 images. But okay. So this is what we do. And one of the things is we have a local Mongo database in our computers stored where the data is being downloaded. And so while it may take you 45 minutes to maybe download that particular data set, if you have it in the database and mine it in the database, you have it in 2 seconds. So this is really super cool. And especially when we are talking about 1,000 virtual machines that you now need to be modifying, you don't have to go out for every single machine if you don't want to have just the status, but want to have some information about that particular machine, such as which operating system runs on. The shell commands, we can switch color on and off, we can switch refresh on, we have a variable management in there. We have a configuration file management that we have included so that you can easily set, for example, CMS cloud equal AWS. We have help, and then we also have, or used to have, this is not yet supported in our current version, high-performance computing interfaces where you can actually run batch jobs. And this is becoming important because there are batch queues exposed in Amazon and so forth. So how do we do this? Well, we install this currently because this is a developer thing. So we have written our own installer that goes out and downloads like 7, 8 repositories. And with a one-line command, students can now specify the installation capability. And it's very easy to install. Naturally, because Jupyter notebooks are kind of popular, all of this stuff can be integrated in Jupyter notebooks. So you can start virtual machines from CloudMesh straight in your Jupyter notebooks. Not only that, you can actually do this on Colab Lab. And there was a discussion earlier today, can I install something? Yes, you can install this because this is a Python package, so you can install it. The database may not be run, but you still can start these things. Here's an example on how we, for example, have an API for Python that you could be running on ColabNet or any other Jupyter notebook. As you see, I have a provider. The name is Chameleon Cloud. Give me the flavors. printer flavors. And the same thing we actually have for images and virtual machines. So this is super easy to use. This one I cannot display you anymore because I'm out of time, but it's essentially the same thing as our CPU example. Here we just take an example that uses k-means as an AI services, and we leverage scikit-learn as one of its underlying mechanisms for developing the operation ID. And you find a lot of information on our GitHub webpage. And again, this presentation will be made available to you on my webpage or on the PyData webpage so that you can figure out all these links and spend hours and hours of browsing. But if you want to spend less hours browsing, you can contact me directly, so there is no problem with this. And we have certain other prototype things, such as, for example, a workflow system, or how do you get, for example, access to a cluster that has GPU machines and stuff like this, and elastic web views, and how do you integrate, for example, Redshift. And we do actually have academic papers, and I don't require you to read them for you getting a good grade. So you already passed because no one has actually left the room yet. So I'm very thankful for that. And with this, I would like to close the presentation.
So there's some questions on the Slido right there, if you wouldn't mind. Yeah, I think we can go a couple extra minutes to let you cover that.
I need to look at this. Well, OpenAPI is really, it's somewhat similar, but it's based on YAML, and so it is specialized for developing REST services.
And if you could read the question.
So the question is OpenAPI similar to interface definition language from ages past? And the difference I actually see is OpenAPI is focused entirely on REST services, and is a specification in YAML or JSON format, and thus easily portable. And so that was this one. Does NIST tell you how you should set up an enterprise data architecture? No, that is up to you guys to define. What NIST simply says is there are these components that could be utilized as part of your architecture, so you will have to pick and choose the ones that apply to you, because NIST would not be allowed to simply say this is how the architecture must look like, but it says this is it could look like. And then does it connect all the legacy systems and data? The architecture does not make any exclusion of that, so that is up to the developer to make sure that this is integrated. I don't know Informatica and MuleSoft, so I don't know what these systems are. So I apologize for the not knowledge, so I can't answer that question. Maybe we can keep this question here so that the person who has this question can educate me, and then I can comment on this. How do students pay or get charged for all the cloud stuff? These days, I only give them the mandate to use the free tier for students on any of the clouds, because of my bad experience I had with this other student, and I can't control the other students. If there's one bad apple in there, it's bad for everybody. And so I have unfortunately changed my model to use only the free tier. So how an enterprise may be charged? If I would be an enterprise, I may actually just focus on one cloud or two clouds, because the cost savings while switching from one to another cloud at runtime or during the program development could be substantial. So they're dependent on which services you need. So certainly this is different. But Cloud Mesh doesn't make any assumptions about that. This restriction comes from me, right? So how do you deal with identity and secrets to access the services you deploy with the Cloud Mesh tool? Right now, the Cloud Mesh tool is a client tool. All the identity management is being done on my laptop. And each one would have to have its own credentials to, for example, go into the clouds. And that's how I switch between them. So that's part of that YAML file. But it could be integrated into some other services, such as, for example, an existing cloud service. Doesn't this tell you how you should? Oh, so yeah, the Informatica and MuleSoft. Can you maybe elaborate what that is? Maybe I know it.
It's just an integration, like an integration tool for an enterprise. You can put in that supposedly connects to all your legacy systems, virtualizes it in a layer.
Yeah, I guess I'm blessed being an academic and don't have to know that particular tool or these things. And maybe I'm not blessed, but I have to admit ignorance here that I actually don't know these tools.
I think you should go with blessed.
Yeah. So I should probably learn about this, and then I may be able to answer that particular question. Yeah.